This is not my first kind of science event. I know it from when I did my PhD back in the UK, and I really love it because I love science communication. I think it's really important to get our research out there so that everyone gets to know what we're doing. So as Karin said, I am a researcher at Stockholm University. I've been working there for the past 2 years, and I've been studying water's double personality. But before we dive into what is water, I really think it's important that I highlight that, yes, I've been here for the past 2 years, but I'm actually part of a bigger thing. This is research that has taken roughly, I think, 5 years and at least 3 different larger experiments here in Korea, what's called PAL. And this is actually the experimental team that has been involved in this research. And here's Anders Nielsen. He's the PI that has led all of these experiments. So yes, I think sometimes people can imagine that scientists are a bit of a lone wolf, but in reality, as you can see, especially us experimentalists, we really need to work as a team. We need to work together collaboratively. And that's how we manage to bring science, to move it forward, really. Okay, so now over our group. Water. Well, basically, water, as we know, is the most common liquid in our planet. We are composed of it. The planet is composed of it. And it's quite unique because, at least for us, we see water as the giver of life. And this is why there are so many efforts in looking for water in different planets out there in space to see if there's anything that could potentially be like life as we know it. However, even though it's incredibly common for us, it is in fact pretty weird. And why am I saying that it's weird? Well, because it does not behave like a normal liquid, actually. It has over 70 different anomalous or strange different properties. And in fact, we're really used to them. One of these typical weird properties that it has is referring to this thing in particular, the fact that ice floats on water. For us, this is the most regular thing, but this is not how a normal liquid would behave. In fact, if we would have a normal liquid, let's say like methanol, and we were to put its ice, so it's solid in it, what happens is that the solid actually sinks. And why is this? Because frequently when you have a liquid and it solidifies, all the molecules start getting all close together, closely packed, the density increases, and boom, it sinks. But as we know, well, this is not what happens when we put some ice cubes in our preferred beverage on a summer day. If we have water like we have here, and then we decide to put some nice ice cubes in it, what happens? Well, yep, the ice floats. This for us is pretty normal, but as I told you, this is actually quite strange because this is telling us that the solid does not have the highest density of water, but rather it's actually a liquid state, the one that has the highest density. And if you were to measure the temperature at the bottom of this glass, you would actually see that it's at 4 degrees. So this is the first anomaly, the density anomaly. And actually at the beginning, when the temperature starts decreasing, our density, well, it starts increasing. Or if it were a normal liquid, it would just keep going, right? But in our case, as we know, after 4 degrees, our density starts going down again, because why not? And this is really important because thanks to this, life can keep going even when lakes freeze. For example, here in Sweden in winter, the lakes are frozen, right? And it's not then like everything just dies and from nothing life will have to start again. No, of course not. We have the ice nicely floating above. We maybe even skate on it, but below that we have water at 4 degrees, and this is where life is thriving. Now, another thing that you might consider is the high boiling point. And this is also quite important. So if we're looking at the periodic table, and let's look at the carbon group here by increasing the molecular mass. You see here we have tin, which is the highest molecular mass, and as it starts going down in molecular mass, so does the temperature at which it boils. Now, if we were to go to the oxygen group here, it starts going down, polonium, tellurium, selenium, sulfur. It all goes pretty neatly. But then when we get to where we would have H2O, that is water, then guess what? Well, it says here that we would expect a boiling temperature of minus 50 degrees. And we actually know that water at room temperature is liquid. So it's definitely not the boiling point. But in fact, it's 100 degrees. Imagine if the boiling point was minus 50 degrees. In that case, then, well, basically, we would not know water as we do. We would not, basically, would all have transformed into vapor. So, sorry about this. What is the reason behind this strange behavior? So one of the hypotheses has been that, in fact, water is not only one liquid, but it's two liquids, hence the dual personality that I mentioned in my title. We would have a lower density liquid and a higher density liquid. So what this means is actually that we have two different, just local arrangements. In the long range, so far away, there is more disorder, but locally we do have a certain arrangement, and this leads to different densities. So for example, in the left, when we have more molecules, we have a more open structure than what we have on the right. So on the right, that would be a higher density, and on the left, a lower density, because the molecules are more expanded, they have more space within each other. Now, where is this weirdness stemming from? Or where could we find it, actually? We could find actually this transition between these two different liquids far, far, far deep down into the phase diagram of water. So basically on this side, we have temperature increasing upwards, and here we have pressure going to the right, increasing. So we know at like a room temperature and so on, we have our normal liquid water as we know it, lovely. And then we start cooling it down. And then we hit the melting point of water, which is, as we know, at least at ambient pressure, 0 degrees. From here, then we actually get into what is called the supercooled state. And no, this doesn't mean that water all of a sudden is wearing sunglasses and feeling really cool. You know, what this means is that we actually manage to cool down water below its freezing temperature without crystallizing. However, of course, it really does want to become crystalline ice because that's the most stable phase. So eventually it does that. So this is actually our problem because it really, really wants to crystallize. And in order for us to see the liquid-liquid transition, which is meant to be found around here, we would have to lift this crystalline curtain and get into what is called no man's land. So basically, this line is telling us where there is the transition between low and high density, or the hypothesized transition. And in my understanding, although there are other hypotheses also about this, I see that no man's land is basically like our uncharted territory because it's so hard to be there without water crystallizing. Just to show you how, like, super cool water, I have a small video because actually you can actually do this basically at home. I mean, for this, I just have ultra pure water and then an ice bath with salt to make it really, really cold. And it's liquid, but the moment that I shake it, it becomes crystalline ice. And why is this? Well, as I told you, it really wants to be in that structure, but sometimes it just needs a bit of a nudge to get there. So if we are to lift this veil of crystalline ice and I have access to the no man's land, then we have to be super fast because crystallization happens at incredible speeds. In fact, if we were to study the water around this temperature, so minus 70, we would need to perform an experiment within 0.000000001 seconds. So you see, we have a very, very tiny window in which we can perform our experiments. So you can imagine that this is not something that you can just do in your kitchen, but rather you need some special kind of technology to do this. And in fact, this technology hasn't been around it for such a long time. Okay, so now we know that we need to be very, very fast. But also, how do we access no man's land? Which is the best route? So there are two main routes that one can take, of course. The first one is going from the top to the bottom. So you have your normal water and then you cool it down. Different approaches have been used, for example, putting it into very, very tiny cavities, using droplets, but we hadn't managed to go far down enough that we could see this transition. But then the other approach is actually rather coming from the top, is coming actually from further down and, hitting our way up. And this is a part that I haven't explained of this lovely phase diagram that I have here. But the thing is that what lies in the depths of this phase diagram is the amorphous, low density amorphous ice or the high density amorphous ice. Now you might be wondering what this amorphous thing actually means. Well, it means that it's kind of solid, but the difference here is that a crystalline material, you could think of it a bit of a parfait or an onion, so you have layers, and so nearby you have a structure, and it actually, if you look far, far away, you can still see this structure over and over and over again, repetitive, Whereas in the amorphous, well, I mean, it is solid, but your molecules are all just like disorganized. Maybe you have some bit of a local order, so maybe things near me are within a certain structure, but if I look further away, it's just absolute chaos, basically. And importantly here, I said that there's an amorphous low density and a high density one. So if I told you before that we have hypothesized about a high density and a low density water, well, I think it's not too far-fetched to think that maybe these amorphous ices are the counterparts of those liquids that I mentioned before. Okay, so now we decided we're going from the bottom to the top. But how on earth am I supposed to get these amorphous ices in the first place? Well, very simple. We just need to pressurize some ice. And of course, we don't use elephants. That would be quite impractical, to be honest. What we use instead is a material testing machine. So this is a computer just for reference on the size. It's considerably taller than I am, even though that's not particularly hard. And so on this base here at the bottom, we put another base and another one. And then we put this cylinder that's surrounded by this copper coil. And through the copper coil, we have liquid nitrogen. And so inside the cylinder, we put our sample, and on top of the sample, we put a piston, and then we just press the hell out of it, basically. So our lovely, nice structure that we had in our lovely crystalline ice, it just gets dead, basically, and we get a lovely amorphous structure. We also use some temperature as well, still very, very cold temperatures, just to anneal it, and some details, of course, but this is the key thing. We just crush it, basically. Yes, and to see the transition actually from the high density to the low density amorphous ice, you can even see it with the naked eye. And here I have a video. Oh, how it looks like. This is our high density amorphous ice. And it's going to sit there for a while. This is at ambient temperature and pressure. And now you can see that it starts expanding, because the first thing that it wants to do before any melting and so on is actually transforming into the low density ice. And we like to call this popcorn ice. I think it's quite evident because it just like kind of pops. However, what we are looking for is not how it looks, if it looks pretty or not. What we want to know is how the structure is changing, basically. So for that, it's also a bit hard. So now we don't only need to be fast, but also we need to look at very tiny, tiny, tiny things. So in the nanometer scale, sort of. So we have like human scales on the left. So this is one of those vessels where you can actually land planes on. So that's like 200 meters. And then at the very bottom, we have the thickness of a human hair, 200 micrometers. So roughly this is the scaling. And then on the biological scale, we will have like this kind of nasty tick thing, which we don't really like, I know, but these are very, very tiny. And then if we compare it to, let's say, the size of, well, in this case, we have as an example DNA, the width of the double chain, then that's roughly the scaling that we have. So it's twice that, you could say, almost, from the vessel to this thing. So we're in this ballpark here, really. So you can see it's very, very tiny thing. So now we also need to be able to measure something that small. And how do we do it? Well, X-rays, of course, but not just the normal X-rays. They're not the same X-rays that we would be using for your dentist appointment, for example, or when the doctor wants to look at your lungs. But rather we need very high intensity X-rays. Now, why are we choosing X-rays anyways? So here is the spectrum of electromagnetic waves in which we actually have visible light. And here's in the micrometer scale. And if you can see, it's a very tiny portion, the visible light. We have very, like, considerably larger waves. We have microwaves and radio waves, which are 1 meter wavelength scale. So you can imagine that we cannot really go into this big size, because if we have something tiny, tiny, tiny nanometer, and I put it down here, then the wave will just like go completely over my structure, and we will not see anything, because we need this interaction, right? So we need to go to the other side. So we pass the ultraviolet, and then we get the X-rays. Now, as I said, not all X-rays are equal. We need something that's very fast and also with high energy. And this we can only achieve in these massive facilities called X-ray free electron lasers, of which there are very few in the world. The first and I think biggest one is in the United States. We have a couple here in Europe. There's one in Japan, one that's being built in China, and the one that we went to in South Korea. So yes, actually we prepare those tiny, tiny ice samples. We put them in a liquid nitrogen container and shipped it all the way to South Korea to be able to make our experiments. So talk about hurdles, right? So how do these X-ray free electron lasers work? And a very broad way to describe them is that you start having as an injector, so you generate your electrons. And then you really want them to go fast, 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 and get more energy, energy, energy through this linear accelerator, kilometers long. And then they get to the undulator. So basically they go around like this, like waves, like roller coaster. Well, basically, sorry, like stay size. And what happens here, basically, they start generating X-rays. And because of this undulating thing, basically you have that they get in tune, the X-rays. So remember that we have waves. So basically this in tune or coherence, as we call it, is basically that the peaks of our waves are on top of each other, and the valleys are also synchronous. And well, eventually, well, we need to get rid of those electrons. We don't really care so much about them for this particular type of experiments. And we get our amazing X-rays that get to the experimental hole, and then we can measure. So now we have fast, high energy, our samples. I mean, it's a bit tricky, but we have our samples. So now we measure. So to measure, also remember we are at liquid nitrogen temperature, so really, really cold, and we wanted those minus 70 degrees. But how to get this? Well, lasers are the answer. So we have here a video of basically what the experiment consisted of. So we have our samples. And what you see here is a grid, and each of these little holes is filled with the ice. And then we shoot the laser to heat them up. First this laser, and then after different delay times, because we want to see how things progress over time, we can then shoot our our X-ray. And then we can measure the signal. And depending on the signal is how we can determine if it's high density amorphous ice, if it has transformed into liquid, if it has become a crystalline ice. So yes, this ring, whilst it might just look pretty to you, it actually tells us about a story about the structure. So what did we see? So we first saw this ring that tells us that we have a high density amorphous ice, which we know because that was our original sample. Then the signal gets broader. We know that it's transforming into a liquid. And then we finally get the appearance of a ring, a second ring here. And that is the low density liquid. And mind you, over here, you only see these broad rings. And this means that we're still not in crystalline region. And eventually it does crystallize as we expect, of course. But we were able to see this transformation of high to low density liquid before crystallization. And this is the relevance of this experiment, because for the first time, it's no longer molecular simulation theory that points towards this being a thing, but we were actually able to see it happening. We were able to lift the curtain of crystallization. Now you might say, yeah, this is happening at very low temperatures, but you were saying that, you know, it's important for life, etc. So what is going on here? So remember that we had this little line between high and low density liquid. Well, if we zoom in here a bit, this is the same line, mind you. On one side, at the beginning, we have low density liquid, and on the other side, we have high density liquid. However, we eventually reach a catastrophe, a critical point from which what we call the Widom line opens, and this reaches ambient conditions. And what happens within this Widom line is that you no longer have a pure high density or a pure low density, but rather if you're here in the ambient conditions, you have mainly high density liquid, but you have some little regions fluctuating in and out of low density liquid. And if you were to go down, then the reverse happens. You have mainly low density and some regions coming in and out of high density liquid. So you have both of them present. So importantly here, ambient conditions. So actually at ambient conditions, we're expecting to see this fluctuation between the high and the low density. So to explain it, I have this nice animation from Anders. And just a reminder, especially in case I start mixing up things with my words, the larger the volume, the smaller the density, and the smaller the volume, the larger the density. Okay, because if everything is compact, you use very tiny space. If everything is expanded, then you use a lot more space. Okay, so first here we have our high density, and it's 100 degrees, all expanded. So low density, and it starts cooling down. And of course, once it starts cooling down, then the density will increase, the volume will decrease, as you can see. I mean, now we're in liquid terms, of course. So it will keep changing here. So we know that it's getting more and more compact. And then we start seeing a little bit of fluctuations with some tiny regions of the blue, so the low density. And then eventually we will get to our 4 degrees. And as we know, 4 degrees is our density maximum. So we cannot compress any further. So if we were to have only high density regions, then how on earth would we be able to all of a sudden start expanding again, right? And this is where our low density regions come into play, really. So yes, we've reached 4 degrees, and then we keep cooling down. And as we keep cooling down, the amount of the low density regions will start to increase, of course, so that our sample starts expanding, that is, the density starts decreasing. And here you see even more evidence now at the negative centigrade value, until you have a large proportion of low density structure and a bit less of the high density ones. So this is actually how this two liquid theory is explaining a bit these anomalous properties of water. So in summary, you can say that water is definitely strange, but it's also the coolest. Thank you very much for your attention.